analysis. Okay, so we are going to call summation, well, moment Z at point A. The whole thing will be equal to 0. So this will be equal to minus 10 times 10 to the power 3. And then you have a distance of 0.15. Then minus by 10 times 10 to the power 3 again. Multiply by 250.4. And then you're going to plus by dy multiply by 0.55. The whole thing will be equal to 0. Okay, so what you see over here, so you have 10 power 3 times by 0.15 plus by 10 power 3 times 0.4. So dy or 0.55 dy, this will be equal to 550 or 5500. So dy 0.55 is also going to be 10 times 10 to the power 3 Newton. Right? And forces, so this will be equal to, so it's going to be AY minus by 10 times 10 to the power 3 minus by 10 times 10 to the power 3 plus by 10 times 10 to the power 3 equal to 0. So AY is equal to 10 times 10 to the power 3 Newton. So there's another way to do this. Okay, you can also specify. Okay, Okay, there's an alternative, a quicker way. Okay, if you are comfortable with this, do it. There's another alternative, is you can specify that AY is also equal to what? Is equal to dy. Y based on geometry and loading. So the axis of symmetry based on geometry and loading is y. Okay, so the left hand load geometry and the right hand geometry together with the loading are the same. That's why you can make this statement. Then you just do summation about forces in your y. Okay, you get the same answer. Okay, so now let's draw our shear force diagram. Okay, so I'm going to sketch the shear force diagram. So some of you, this is might be the first time that you see it. It's okay. We're going to do it a lot more. Maybe after your term test. Okay. So this is your V. So now you know what you use your V for already. Okay. Your shear stress, your shear force. You can calculate your shear stress. So this will be your X. So this is 0. Then you have 0.15. Then you have 0.15, 0.4. And then you have your 0.55. Okay, so 1.5, 1.15. Okay, 0.55. So you have your 10 over here. Now here's minus 10. So from 0 to 0.15, right? So you will have 10 kilonewton coming here. Right, so this is your 10 kilonewton. And then at point B, it comes out by 10. So I should draw this darker or use a different color, right? 10. Then it comes out by 10, right? Then it goes through 0. And then at point 4, it's at point C. Then you have another 10. Okay. And then use horizontal. So this is your shear force diagram. Okay, so down here is where you have your minus what? 10. So that is your shear force. Then we look at our bending moment. Okay, so this is what we call our shear force diagram. Then we look into our bending moment. Right. So a bending moment, so this is M. Okay. And then over here, I'm only going to focus on the positive side. I'm not going to focus on the negative. I'll tell you why later on. So again, this is 0.15. Over here is 0.4. And this is 0.15. Right? So how this will behave is you will have positive, right? So you will have a slope going up this way. Then from 0.15 to 0.4, it's going to be a horizontal. And then it's going to come down this way, right? So at this point, this is where we call our point E. Okay, it is called our point E. So at point E, what is that moment? Okay, why I pick point E? Because it's at point E where it's going to fail. Okay, so we are going to do static analysis. Okay, so we're going to draw the diagram up to point E. All right, so we draw from point A to point E. Right, so we know this distance over here. This magnitude is 10 times 10 to the power 3 Newton. And then we have another load coming down. So it's somewhere around here. Right, 10 times 10 to the power 3. So we also know that the distance from here to here is equal to 0.15 meters. Okay. And then at point E, right, at point E, we're going to do two things, okay? We're going to call the shear force at point E. We're going to assume it to be down. So for now, I'm just telling you, we're going to assume it to be down. And at this point, we're going to assume it to be moment at point E. Okay. So some of you might ask me why down. So later on, I'll explain to you why this direction. Okay, because it's in the next chapter, not on this one. This is, but just to let you know, this is what we call, we assume. Okay, we make assumption, we assume positive shear and positive bending moment. Okay, that's what I assume. So now we have to find out what's our distance from here to here. Right, so that distance over there is what, 250. So it's 0.125 meters. Okay. So now we are going to take the moment at point E where I'm drawing a dot now. Okay. So we're going to do static analysis. Okay. Where summation moment Z at point E, the whole thing will be equal to 0. Okay. So the 10 kilonewton, the furthest away is minus because it's going in a clockwise direction. Multiply by 0.15 plus by 125, 0.275, right? And then plus by 10 times 10 to the power of 3, right? Why plus? Because the one that we are doing now is going to do anti-clockwise from this point over here, okay? From this point over here, right? Multiply by 0.125. And then plus by moment at point E, okay? Moment at point E. The whole thing will be equal to 0. So moment of point E is equal to 10 power 3 times by 275 is equal to 2750 minus by 10 power 3 times by 125 is equal to 1250. So moment of point E, 2750 minus 1250 is equal to 1500. So positive 150 Newton meter. So when it's positive, means the direction is valid. Okay, means this direction, when it's positive, direction is valid. If it's negative, means it's not valid. So now we know that this value over here, moment at point E, right, is equal to 1500 Newton meter. Okay. Now some of you might say, Eugene, at point E, right, the shear stress is equal to 0. Why would it fail at point E? Right. So the answer is very, very simple. The answer is simple. Why? Is because moment at point E, the moment is going to fracture the structure, and it's not because of the shear force. Okay, repeat again. Okay, the moment will fracture the structure. Now, so from here, we have found our, so what we have achieved. We have drawn our free body diagram. We have drawn our shear force and bending moment diagram. Next, we're going to find the centroid and the second moment of area. We're going to do that next. Okay, so I'm going to do this directly over here. Before I go on, anyone, any questions, please? Anyone? No question? Okay. So for this case, we are going to find the centroid. Okay, find the location of the centroid. Okay, so we are going to, I'm going to sketch this out. Right, so then so for this case, it's not so straightforward where the centroid is. We have to find. Okay, so how are we going to find it? So this is, I think you guys have found centroid before. Am I right? We have done examples where you find centroid. So this is your Y. This is your Z. Rotation about X. Okay, so we know that for our case, the moment is in Z-axis, right? So what we want to find, okay, so find the centroid, okay, and later we want to find IZZ, okay, because the rotation, the moment is rotating about the Z-axis, okay. So we know that this will be our ZZ axis. Now I don't know, so this position is the position of our centroid. Exactly where, I don't know. I only know the orientation is that direction. Okay, so we're going to take the datum from the bottom. Okay, and I'm going to divide this way. So this is my point 1, section 1, section 2, section 3. Okay, and because that is the orientation of my centroid, I now declare, okay, that over here this will be my what? Width direction, and over here this will be my depth direction. Okay.